Hello everyone, and welcome to our first NEPSI Tech Talk. We are very excited to kick off these sessions with you today and to thank you for joining us. We hope that you find this format convenient and user-friendly and that you will walk away knowing a little bit more about reactive compensation. As far as some housekeeping, these sessions will be recorded so that you can refer to them later. If you have any questions along the way, please use the YouTube chat feature. Matt Marcette is here with me today to keep me alerted to any chat messages that come in, and he's also helping to make sure that things go smooth technically. Thank you, Matt, for your help. Also, please feel free to follow up with us after this session if you have any additional questions or would like some additional information. And if you have any ideas for future Tech Talk sessions, please let us know that as well. We want these Tech Talks to work for you. Let us know what you need. So to jump right in today's session, we would be talking about the requirements for harmonic filtering when high pulse drive AFE drives are utilized. At the end, we expect that you will understand what harmonic filtering is required, when harmonic filtering is required when applying these types of drives. So let's get started. So I often get this question when I get phone calls about high pulse drives and AFE type drives. Oftentimes the customers will say, hey, they're IEEE 519 compliant. I have nothing to worry about. They want to install power factor correction and they're going to install standard capacitor banks. And oftentimes they would say, hey, what's the big deal? I have AFE drives. They're compliant and I have nothing to worry about. So the answer to this question in short is yes, there are some things to worry about, and today we're going to discuss some basics and then get into why you need to worry about it and when you need to worry about it. So first some information about drives. So again, this presentation is about 6, 12, and 18 pulse drives. High pulse drives are normally considered 12 and 18 pulse, and the lower pulse drive, 6 pulse drives, would be considered a low pulse drive. So when we talk about pulses, what we're talking about is the number of diodes on the front end of the rectifier. So a bridge rectifier, when it's a 6 pulse drive, is the simplest form of drive. You can count that there's 6 diodes here. This diode bridge converts AC to DC and puts it onto the DC bus. And from there we have an inverter that converts it back to AC, and therefore we can control the speed of the motor and also the torque of the motor. So a 6 pulse drive, it will chop up the current in a fashion similar to this. And actually the amount of chopping that you get is related to the impedance in the front of the drive. You often hear about inductors on the input, line reactors, 3%, 5%, and so on. So the lower the reactance, the more chopped up the waveform will get. But 35% THD is pretty typical. In higher pulse drives, when you go to 12 pulse and 18 pulse, you can see here on the right that the input current waveform gets smoother, and therefore the THD, the harmonic distortion, will go down. And likewise, on 18 pulse drives, you can count that there's 18 diodes on the input. You can also see that there's a transformer, 4-winding transformer on the input. And the sine wave, the 60 hertz sine wave is relatively smooth. So it's almost harmonic free, it's only 3%. These drives, as you go up in pulse number, you also go up in cost and in complexity. And that's something to always think about as you're applying drives, is that if you go to 12 pulse or to 18 pulse, you're going up in complexity and also in cost. And this type of drive, unlike the AFE drive, can have a poor power factor. So also it's something to think about. A standard 6, 12, and 18 pulse drives typically have a worse power factor than an active front-end drive. So when you look at the 6, 12, and 18 pulse drive, oftentimes it's considered to not have harmonics at the lower harmonic numbers when it's 12, 18, or 24 pulse. So you follow this typical equation here for developing what harmonic content exists within the drive system. So a 6 pulse drive will put out 5th, 7th, 11th, 13th, 17th harmonics, and so on. So we have a component at the 5th and 7th. A 12-post drive, theoretically, and again, theoretically, should not put out 5th or 7th harmonic. And you also see that there's other harmonics missing also, the 17th and the 19th. We skip a band of harmonics as we go up in frequency. And the 18 post is even better. We have our first harmonic starting at the 17th. So we eliminated the 5th, 7th, 11th, and 13th harmonics. So these drive systems are more expensive and they produce less harmonics. The reality, though, is that these drives do put out harmonics at the frequencies below the 11th. The 12 post will put out some 5th and some 11th harmonic. And it's important to understand that this does exist. In theory, it should not, but in reality, it does. And that small amount of harmonics that these drives do put out can be of concern. And we're going to talk about that today, that small amount of harmonic current. The active front-end drive, instead of using diodes on the front end, it uses an active front end. And what that means is that the active front end can modify the shape of the harmonic current, the shape of the current waveform flowing into the drive. And therefore, it can actually mitigate harmonics, reduce the harmonic current distortion into the drive. It can also correct the power factor. So oftentimes these drives operate with a near unity power factor, and they also have the ability to do regenerative type control, where they can export power, and like in a crane operation. So one of the things that's interesting about the active front end drive is they utilize an LCL filter on the front end because of the switching frequency associated with the front end of these drives. That LCL filter consists of capacitance and reactance. And when doing harmonic studies, it's important to actually model this front end of this active front end drive, because it is a small amount of capacitance and it will create a resonance in your system. I just ran into a project that had that going on. It was a crane operation project. So it's interesting to note that resonant condition can occur and it needs to be modeled. It forced our system to go from a normal notch filter to a high pass type filter system. So a common misconception here is the AFE drives are IEEE 519 compliant, and therefore I do not need to worry about power factor or harmonics within the plant. The reality, though, is that in most situations the AFE drive is only a portion of the total plant load, and that there is still a requirement for power factor correction. So to gain a better understanding of when AFE drives and high post drives need to be equipped with harmonics, it's important to actually understand the basics of harmonics. And so what I've done is I developed a very simple system. In this case, I have a source impedance that consists of an 8 Ka short circuit. I have a service transformer here, which is 10 MVA and 7.5%. And I show a 5,000 horsepower drive. So this would be very typical of a pump station or a compressor station used in oil and gas. You might have multiple 5,000 horsepower motors that are being utilized to control the flow of gas or oil within a pipeline. So this system, this three-phase system, can be represented here as a single-phase model. And the harmonic current produced by the drive is situated over here, and that's an ideal current source. And when we talk about ideal current sources, what it means is that no matter what the impedance here is of the source, this harmonic current will flow into it. So to go on to the next slide, we can assign impedance values according to the representative system that we have created here. We calculate a source impedance utilizing this method here, and we calculate the transformer impedance utilized here. We're reflecting everything to the 13.8 kV bus. So these impedance values here are based on the 13.8 kV viewpoint. It's important to remember that whenever you're doing these type of calculations, that we're doing it at 60 hertz. It's a 60 hertz representation. It's a single phase representation of the model. And in this case, you have to remember that the inductive reactance of the system, XLN, which is the value of 0.1 ohms here and 1.42 ohms here for the transformer reactance, is impacted by frequency. If we go to the second harmonic, the inductive reactance is double because it's N times XL. So inductive reactance, remember, is equal to 2 pi F, which is frequency, times L, which is inductance. So we can further simplify this model into a single impedance. We added the R's, the resistances, and we added the X's, and we have a single impedance model. Very simple here to realize that the harmonic voltage generated by this harmonic current source is equal to I times X and I times R. It's very easy. It's just Ohm's law. We can take the impedance values that we measure and multiply times current and come up with a voltage. That voltage is line to neutral voltage. You can also calculate ITHD, ITD, and VTHD from this very simple model. Down here, I have shown the impedance line, okay, versus frequency. So on the x-axis, I have harmonic number, and on the y-axis, I have ohms. So looking from this viewpoint, from the secondary bus into this impedance, I plot a straight line because it's, again, is XL and equals N times XL. It's very simple. So it's just a matter of applying Ohm's law at each and every harmonic, 5th, 7th, 11th, 13th, and we can easily calculate the voltage distortion at this point. So what happens when you add a capacitor bank to the system? And what we show here is the addition of a very large capacitor bank. What happens? Okay, so we've added the capacitor bank here. It's 5 megavars, and what you got to remember is that a capacitor is different than a reactor. And a capacitor, the impedance of the capacitor will drop with frequency. The impedance drops with frequency. So we represent that here with that green curve. We have a drop in frequency. So we have our original transformer impedance line here in red, and we have our capacitor impedance here in green. There's a crossover point, and that's called resonance. And that's easily calculated utilizing these equations here. So we have X of C, the capacitive reactance, is equal to the line-to-line voltage squared divided by the megavars of the capacitor bank. And we have a situation here where with 5 megavars on in this system, we have a resonance right at the 5th. Okay, and the resonance created by the capacitor and the inductive reactance creates a high impedance. So again, when we're looking into the system from the secondary, we're seeing the impedance as developed by this magenta curve. So we have the same current injection, right? Current times impedance will give us volts. And you can see here that we have nearly 600 ohms of impedance created by that resonance. 600 ohms of impedance, which means that any value of current, even a very small value of harmonic current present at the 5th, will create a significant amount of voltage. So let's say, for example, I have a drive system and it produces 1 amp of harmonic current at the 5th. It would be 1 amp times 600 ohms would be 600 volts. That would be my line to neutral harmonic voltage. Okay, and that will be represented in a VTHD of 7.5%. And this is already unacceptable. Generally speaking, we like to maintain at least or no more than 5% voltage distortion on a system. The peak of this resonance here is calculated utilizing this formula, and it's X of C squared divided by N being 5 in this case, okay, because it's a 5th harmonic resonance, divided by the resistance of the network. The resistance of the network is very low, and therefore we have a high impedance. Because we have a lot of voltage created at this point, you can also see that a lot of current will flow into the capacitor bank and also into the system. On multi-stage banks, and most industrial plants utilize multi-stage capacitor banks, you will create a resonance for each and every step that you put on. I've already showed that there's a resonance at the 5th for 5 megavars, but what's interesting here is for 1 megavars, as shown with the magenta curve here, I have 11th harmonic resonance. And again, here we have an impedance well over 1,000 ohms, which means just 1 amp of harmonic current at the 11th harmonic will create over 1,000 volts line to neutral. And that's significant. That's a system that will not operate. So what happens during resonance? We get current amplification. And what I show here is that you have up to 80 times current amplification from a drive. So if you have a drive that's putting out very low levels of harmonic current, but it corresponds to the resonant frequency of your network, you can have a significant amplification of harmonic current. And really the key point here is that we have amplified the current in many regions, not just near resonance, but in all of the regions shaded in red. All those harmonic currents are being increased in magnitude. So at the 5th here we have a significant increase, but also at the 7th we have a significant increase. And at higher frequencies we continue to have increases in harmonic current. So even though an AFE drive or high pulse drive may be putting out low level harmonic currents, we are amplifying that harmonic current represented by the red zone here, the red arrow. We're amplifying harmonic current in that region. So we have a very low drive output here represented, but when that flows into this resonant circuit, which is the resonant circuit formed by the metal enclosed cap bank and the source impedance, I get this amplified current. The point of common coupling, incidentally, is between is within this impedance, is basically on the primary side of the service transformer, but that would represent an area here or here, would not matter. And you can see that that's in the amplified section of the circuit. So even in a situation where you might be using a high pulse drive, you're going to have amplified current and you may easily exceed the requirements of IEEE 519. So it's key to understand that when applying capacitor banks in an environment that's using high pulse drives, there's a good chance that you will exceed IEEE 519 because of resonance amplification. We've also shown that voltage distortion can easily exceed 5%, and that's above and beyond what would normally be considered acceptable, that 5% value. I've taken an example. We have a major drive supplier who has supplied some data, and this is a pretty good representation for what you could expect for drive harmonic currents for both an 18-pulse drive and an active front-end drive. One of the things that's interesting to note is the 18-pulse configuration has about a 0.95 lagging power factor. The active front-end has a near 1.0 power factor. So you do not need to add capacitors for the active front-end drive to get the unity power factor, but you may have the balance of the plant to worry about. So I have done the calculations for the condition of the 5th harmonic resonance that we previously shown. What we show here is that the 18-pulse drive will put out 1.1% of distortion at the 7th and 2.2% at the 5th. And it's the 5th that we're concerned about here. So I've done the calculations over here. For the 18-pulse drive, I have 2.2% harmonic distortion based upon its fundamental current of 156 amps here, and I have a result I have 3.43 amps. For the AFE drive, the active front-end drive, I have 5.77 amps. So not a significant amount of harmonic current, and oftentimes you would hear engineers say, well, it's only 3 amps or it's only 4 amps. I have nothing to worry about. But the reality, you do. If we do the calculations for the 18-pulse drive, you'll see here that you have 2,000 volts, near 2,000 volts of 5th harmonic voltage, which equates to a 25% total harmonic distortion, VTHD. For the active front end, it's even worse. We climb up to 43.4% VTHD. So yes, you do have a problem. When doing power factor correction, always consider even the low harmonic output from drives, because those low harmonic outputs can create a significant amount of voltage distortion. So what's the solution? The solution is to add filters to the system, and that's what we show here. We put it in inductance or reactance in front of the capacitor bank. Now that inductance is typically about 1/25th of the capacitor reactance, and therefore the harmonic filter still produces reactive power, but it's preventing resonance. And that's key to understand. Harmonic filters are put on the system for a multiple number of reasons. One is to prevent harmonic resonance. Another is to do harmonic filtering. Another is to do power factor correction. But by far, harmonic filtering is probably the third reason why filters are installed nowadays. The number one reason is power factor correction. And that's the purpose of one of the key reasons filters are installed. So power factor correction, prevention of resonance, and then harmonic filtering. You can see here what this filter does to the impedance curve. The red dashed line represents our original impedance line of the transformer. The magenta curve represents the harmonic filter. This happens to be a 4.7th tuned harmonic filter, which means it's got a low impedance at the 4.7th harmonic, and then from there it climbs up. You will note that there's a resonance below the tuning point. This always exists in every harmonic filter, whether it's a detuned cap bank, a detuned filter bank, or any type of filter. There's a resonance that exists below the tuning point. This needs to be addressed. It is why harmonic filters are tuned to a low frequency, typically the 5th or below, is that theoretically there should be no harmonic currents at a frequency lower than the 5th harmonic. So in conclusion, high post drives and AFE drives are a great way to reduce current distortion within the plant, and will keep an industrial plant within IEEE 519 limits, as long as no capacitor banks are utilized. And that's the key message here. If you're installing AFE drives, if you're installing high post drives, you need to, and you're installing capacitor banks, you need to consider the effects of the capacitor banks. The resonance within the system can easily cause your system to exceed 519, can cause the voltage distortion to go well beyond a 5% distortion level, and can cause problems within your network. When you're looking at a system, there is some economic analysis that you should consider. When power factor correction and driver applications are required together, consider a system-wide approach to looking at costs. Consider these options. Option 1, the low-cost, simple 6-post drives. Remember, the 6-post drive is simple topology and very simple technology. And then install a higher duty harmonic filter. So instead of buying an expensive, more complex drive, consider buying a 6-post drive and installing larger harmonic filters, because power factor correction is a very economical choice. You can also consider higher cost drives and lower cost, lower duty harmonic filters. But what we have already shown is that if you install a capacitor bank on the system, you are more likely to have a harmonic resonance issue, and therefore you need to install some type of detuning. The cost to go from detuning filter system that has a low duty to a detuned harmonic filter, or a harmonic filter that has a high duty, is very insignificant. So there really is an economic analysis that should take place when considering high post drives and active front end drives, and comparing that to buying a more expensive, higher duty harmonic filter. So, well, I think that's about wraps it up for today. Thank you so much for your attendance and participation. And again, please feel free to reach out to NEPSI directly for any additional information. Next week, we'll be talking about transient inrush current associated with capacitor bank switching operations. Let your friends and colleagues know that NEPSI is here for you. See you next week. And I will check for questions.